Well, good morning, everybody. Today, we are going to wrap up our discussion on incompressible frictional flow. We'll work a couple examples. I'll do a brief recap on friction as it applies to incompressible flow and answer any questions that you may have regarding the concepts that we've discussed this week, as well as how to work and solve the problems for homework. So with that in mind, let's go ahead and jump over to the notes and start our discussion. Incompressible frictional flow. So this week we've mainly been looking at how to fully solve the mechanical energy balance. Now accounting for our wonderful friend, frictional dissipation. And with this, we've identified that friction is composed of several parts, mainly skin friction, which we can calculate times 4 times a friction factor, times u squared L over D, for L over D, make it simple, plus any sort of losses due to flow expansion, any losses due to flow contraction, and any losses due to the existence of fittings in our flow system. Each of these is a function of the kinetic energy of the system or the velocity head. And with this in mind, we can solve for the friction that we have within our system as we define it via the mechanical energy balance. Most often than not, what we're really looking for, or at least what ends up being slightly time consuming, is solving for skin friction. The most straightforward way to identify skin friction is we would like to determine our Reynolds number using our rho ud over mu equation. And based on this, we have to ask ourselves, is it laminar or turbulent? If it's laminar, we can use the Hagen-Poiseuille, where we can identify our pressure drop as 32 u mu L over D squared. So if I want friction, I can divide that all by rho. And for turbulent, we have to identify a relative roughness factor. And use our empirical models or figure 510 for F, which with that in mind, we can then solve with our friction, where delta P is equal to 2F rho u squared all over D. So that's kind of the process in terms of solving our mechanical energy balance for any terms of interest, where the big hangup can often be within our frictional dissipation, where we have to identify what flow regime we're in. Based on the flow regime, it can dictate how we solve. One other thing we consider with laminar flow, or we can simply approximate our friction factor as 16 over the Reynolds number, and then solve similarly using this method. Any questions over this system and how friction is incorporated within our mechanical energy balance? All right, if not, then let's move on to the last points of consideration, mainly considering flow in non-circular systems or ducts. Ducts, it can be trenches, ditches, things like that. So at this point, we've been really considering flow through a pipe, and by a pipe, I mean a circular pipe with a known diameter d. However, we can also consider flow systems, which are square or rectangular in nature. And so with this in mind, we cannot simply just guess an approximate diameter. We have to calculate what's known as an effective diameter through means of what is known as a hydraulic radius. So for a system that is non-circular, mainly rectangular in nature, we can calculate a hydraulic radius, which is denoted R sub h, which is simply the area or cross-sectional area divided by the perimeter of the system. So this is cross-sectional area. And this is the flow perimeter.
Is that just P for perimeter?
Yeah, that's why I call it L sub P. And with the hydraulic radius, we can calculate the effective diameter by 4 times R sub h. Which you would find if we use this approach for flow through a circular pipe, the effective diameter would be simply the diameter. Or we can also write it 4 times A over L sub P. Some other flow considerations we can consider, because there's all sorts of things, is flow through what's known as an annulus. Which is essentially if I've got flow in this secondary, this is going to get messy, I apologize. Outer region, where I have some inner diameter d sub I and an outer diameter d sub 0. So similarly, I can solve for a hydraulic radius here as the difference between the inner diameter and the outer diameter divided by 4. Any questions on that? Luckily, fortunately, it's fairly straightforward for the most part.
So would this be like something like a triple tube or something where you've got flow on the inside and flow on the outside of your pipe?
This is really going to apply when we start talking about heat exchangers, and we have to consider flow considerations in those systems where you have double pipe and shell and tube. Now, mainly this is going to be more applicable for double pipe heat exchangers over shell and tube, but that's really applicable in these types of system. So with this in mind, let's take a look at an example. And this one says, saying a horizontal ventilation duct 20 feet long and 2 feet square is going to be replaced by a new duct with dimensions 2 feet by 4 feet. So due to complications of installing the larger duct, the new duct will only be 30 feet long. So if the overall pressure drop remains unchanged, by what factor does the airflow rate increase in the new duct? All right, so let's jump over back to our notes and let's see what we can do with this problem. So we have this example is about replacing ductwork. So originally we had a 2 feet by 2 feet by 20 feet section of duct, and it's going to be replaced by a new system or a new duct design that is 2 feet by 4 feet, but 30 feet long. So a couple things we can calculate right off the bat is the effective diameter for each of these, which is going to be 4 times the area over the perimeter. So for this system, the area is going to be 2 feet squared. The perimeter is going to be 8 feet. For this new system, the area is going to be 2 feet by 4 feet, with the diameter or perimeter being 12 feet. So for the first system, we get an approximate effective diameter of 2 feet. For the new system, our effective diameter will be slightly larger at 2.67 feet. So there's a couple ways that we can do this. The most straightforward way is, since the pressure drops and each system should be the same, we can do what's known as a base comparison between these two systems. Meaning, if I can calculate the pressure drop as 2F rho U squared L over D, I can state that the difference between each system should be unity. So what I typically do in this situations is I ask myself, based off of this comparison, which quote unquote terms would cancel. So this is just a constant. Now, if I could argue that my friction factor may or may not be unchanged by this increase in flow rate, what I can do for now is basically assume F is unchanged, and then I can check my assumption after the fact. So if I assume F is unchanged, I can assume my density isn't going to change dramatically. And so what I'm left with is this expression here that says delta P2 over delta P1 is equal to U2 squared L2 times DE1 over U1 squared L1 times DE2. Does everyone see how I was able to simplify my expression? Yes or no?
Yes.
Okay.
Yes.
All right. So now I'm left with an expression that is telling me my change in pressure is primarily going to be consisted of looking at changes between three variables, mainly my velocity, my length, and my diameter. However, the expression wants to know by what factor does the airflow rate increase in the new duct. So what I can do is I can remove my velocity or substitute velocity and input flow rate in my expression. And the way I can look at that is I can state my flow rate of 2, or any system, is simply my velocity times my area, which is equal to the velocity times pi times the diameter, or the effective diameter, squared over 4. So if I solve this for my velocity, I can say that 4 times my flow rate divided by pi times my effective diameter squared is equal to my velocity. So I can put this here, and at the same time, I can write a similar expression here. Or I'll just do this. I'll use a different color to kind of show the action. So I can substitute these two terms in my expression. And so I have the change in pressure comparison, which is simply 1, is equal to, what do I have? 4 times V2 divided by pi squared times length times the effective diameter divided by 4 times V1 over pi dE1 squared times length times effective diameter. So what I'm doing here is I'm looking at, I'm trying to identify that comparison between my flow rate and my pressure drop. Once again, I can cancel out the constants and simplify my expression one more time and say, based on my pressure comparison, I have my flow rate squared times length times effective diameter. No, I forgot squares here, didn't I? Yes, I did. So this would be D. Oh, there it goes. It canceled, crashed. Hold on. I'll bring us back. So yeah, this can get a little convoluted in terms of the organization of the terms. So I basically squared each of the terms. If I square the 4 and the pi, it still gets canceled by the bottom. And so what I'm left with is this expression, which is simply the flow rate squared 2 times length times diameter 1 to the 5th over flow rate 1 squared length 1 times diameter 2 to the 5th. And so what you can see here is without actually having to do my mechanical energy balance and solve for those pressure fluctuations, I can simply do this exercise to look at, based off the key terms, what are going to be the primary factors in changing this pressure for the system that I've identified. We'll use this a lot in design too. However, I think it's really worthwhile to illustrate this technique here, because I know what L1 and L2 are. I know what my diameter, effective diameter 1 and my effective diameter 2 is. And so that means I can solve for the change in flow rate without actually having to put any values in my expression. And what I'm left with is this final expression, delta P2 over delta P1 times L1 over L2 times DE2 to the 5th divided by DE1 to the 5th, all of that square rooted. And that's just rearranging this expression here to solve for my V2 over V1. So what I'm left with is 1 square root of 1 times 20 feet times 2.6 feet squared divided by my 30 feet divided by diameter 1, which is 2 feet squared. Now, I will say that the units aren't going to work out primarily because we've done a lot of variable cancellations. So in this type of analysis, you don't have to worry so much about the variables.
So, oh, you're changing it.
Yeah, this is to the 5th. Oh, why does that keep crashing? Oh, it's because the system's overheating. The back plate's blocked. Oh, I apologize.
Could you explain again why the units don't work out?
The units don't work out in this case primarily because the way I've done this analysis, I've canceled out a lot of key terms. And since we've canceled out some of those terms, the variables may or may not align properly. Because what am I left with? I'm left with essentially, well, actually, in this case, it does, because I'm left with a unitless value since we're looking at a comparison, which is what I should expect. So, never mind. This should be unitless because I'm looking at cubic feet per second over cubic feet per second. And then under the radical, I have feet to the 6th divided by feet to the 6th. Okay, now that does work. And so, let's see, what does this value end up being? I get about 1.68, or the volumetric flow rate increases by 68%. Which, one thing we could look at and consider is our assumption of F being constant. Now in this problem, I didn't give you a flow rate. And so if you had a flow rate, you can check that F assumption. But since a flow rate wasn't provided, I can assume F is unchanged, and I could assume if this is my figure 510, the Reynolds number is going to be pretty high, so such that it's leveled off high enough. Any more questions on this one? This one's a little different than what we've looked at previously in terms of the more traditional problems to solve. But hopefully by now you've learned to not expect the typical when it comes to problems that a engineering professor would throw at you. But does the problem and the solution make sense? Do you guys understand it well? Okay. So let's look at maybe one or two more problems with today. How about we consider looking at flow by gravity? This is an interesting civil engineering problem, and as we know, they need all the help they can get. So luckily, they've got their chemical engineering friends to bail them out of, tough things like Chem 1 and Physics 1 and all those wonderful things. So let's consider that we're going to design an irrigation ditch. And this irrigation ditch is going to be designed such that it's going to be 6 feet wide. It's going to be 6 feet tall. And the state's going to say that for most systems and the way it operates, they want a maximum flow rate or fill height of 4 feet. So with this in mind, the ditch has to be able to handle a flow rate of approximately 50 cubic feet per second. So the question then becomes, if in this worst case design where we've got 6 feet of water by 4 feet high, moving 50 cubic feet per second of water, what is the angle or the drop of this ditch in order to handle this flow simply by gravity? So for this basis, I'm going to be looking at a length of 100 feet. So in 100 feet, in terms of the distance of this ditch, what's going to be the depth or the drop of this ditch per 100 feet in order to make sure that we meet this standard that the state has set? So 100 feet. So for this type of problem, what we could do is do a mechanical energy balance. So based on this, what terms can we cancel out of our expression?
Couldn't we cancel work?
We can cancel work.
And what about the pressure drop?
Yes. It's open to the atmosphere. Anything else?
I didn't see friction mentioned, so can we cancel the friction?
No. You could last week, but not this week.
Okay.
For this system, I would also cancel my velocity, assuming I don't have to worry about if I'm looking at a comparison in this ditch flow, I could assume both sides are flowing at the same velocity. So what we're really looking at here is saying what does the change in height need to be to overcome our frictional dissipation. And in this system, I don't see any expansion, contractions, or fittings. That would be too hard for civil. So we're only going to have to worry about skin friction. So with it being 50 cubic feet per second, I'm going to assume that it's going to be turbulent flow. That's a little fast. I would guess. And so I would say this frictional dissipation is going to be of the form 2F U squared L over D, but now once again, I made it hard in that we have to look at our effective diameter. So we need our diameter, our velocity, and our friction factor. Fortunately, I was generous enough to give you a basis for length. However, I could have just as easily asked this same problem and made you come up with your own basis for length. But for the sake of time, I did not. So we can say L is equal to 100 feet, partial credit, please. So we need to solve for our effective diameter, which for the system is going to be 4 times the area over the wetted perimeter, or 4 times 6 times 4 feet divided by the wetted perimeter, which would be 12 plus 8, or 20 feet. So for this system, I've got, let's see, 24 times 4 divided by 20. So we got a wetted perimeter of, or effective diameter of 4.8 feet. Now to solve for my velocity, I simply look at the flow rate over the cross-sectional area, or 50 cubic feet per second divided by my area, which is 6 feet times 4 feet, or 50 divided by 24, and approximately 2.08 feet per second. With this in mind, I can then solve for my Reynolds number. which my density of water, 62.4 pound mass per cubic feet. If you haven't figured that out by now, you can just remember maybe 1. The velocity was 2.88 feet per second. The effective diameter we solved for as 4.8 feet. And the viscosity of water in English units, 6.72 times 10 to the minus 4th pound mass per feet second. So we do this math. We get 927,000 for my Reynolds number. So for this system, we have a Reynolds number. We would need possibly a relative roughness, which if I didn't give you a material to identify a relative roughness, what would you assume for this stitch?
Concrete.
There you go. Concrete. Yeah, it's the civil engineers. They just sell concrete and concrete accessories. So what I would assume concrete with a K value of approximately 0.01 feet. Let's just do worst case scenario. So my K over D value would be pretty high. So 0.01 divided by, so 4.8 feet was my D, 0.002. So from figure 510,
Hey, Aaron, will you mute your mic?
I got an
We have
F.
one more pack. Well, actually, there's another like half one that was open.
There, I got it. I can tell she's paying very well attention. So with this in mind, and our Reynolds number of about 900,000, I see we have an F value of approximately 0.0059. So now I have my friction factor, my velocity, and my effective diameter. So I can solve for my friction term is 2F U squared L over D, or 2 times 0.0059 times U squared 2.08 feet per second squared times 100 feet divided by the diameter, which was 4.8 feet. This should give you your answer in feet squared per second squared. Which is 1.06 feet squared per second squared. So with that in mind, if that's the frictional dissipation we have, which is surprisingly not as much as I expected, and that would also G equals delta Z. So our height change in this 100 feet is simply the 1.06 feet squared per second squared divided by 32.2 feet per second squared, which would be fairly small, 0.033 feet, which is approximately 0.4 inches. So fortunately, they're wasn't a ton of friction there. So we only need a slight change in elevation per 100 feet to ensure adequate flow. Any questions on that problem?
Do you mind pulling up figure 5.10 and reviewing how to go over the frictional factor? Because when I went to work examples by myself, I was like, wait, how do you actually read this thing?
Yeah, I'd be happy to. So for this, I wish I knew how to make PowerPoint let me draw. So our relative roughness factor was about 0.002. So we need to look at the intersection of this line and a Reynolds number, which in this case was about 900,000. So this is 10 to the 5th, so 100,000, so 900,000 is here. So I would look for the intersection between 0.002 and 900,000, which is right here, which is just shy of 0.006. So I would call it 0.0059.
So it's the curved lines that go up, correct?
Yeah,
that you're
these,
following?
yeah, I can follow this to the
Okay.
intersection of the Reynolds, or I follow the Reynolds to the intersection of the curved lines. A lot of times I just follow the curved lines because it's a lot easier. Because there's so many lines, you kind of lose track of them.
I think it's the fact that they have horizontal straight lines that go across it that was confusing me.
Yeah, like I said, this is probably in the top 5 world's most quote unquote helpful but equally ridiculous figures in the world of chemical engineering. It's right next to the psychometric charts. Any other questions that you guys might have about incompressible frictional flow? All right, if not, I think I'm just going to cut class today. That's all I have. And so next week, we will take a look at compressible flow. Don't forget, I did push back the homework because some of you had exams and were stressed, and I get that. And if I haven't responded to an email of yours, I will respond hopefully by the end of this morning by noon today. And as always, if you need anything, feel free to reach out. But if not, take care, guys. Have a great rest of your day and have a great weekend.
Dr. Lopez.
Can I ask you a question about the homework?
Sure.
Can I ask you a question about the homework? Okay, so just pretty much when it says a pipe and it isn't specifying, if we're making like, for example, question 2 through a 2-inch pipe, if we're doing that, do you want us to just specify like what pipe we're assuming to get the friction or
Yes.
the K values? You know what I mean? Just
Yes.
say like assuming. Okay. All right. And then I think that was it. I have to do the Excel iterations for question 2 again. All right. Thank you.
You're welcome.
Dr. Lopez, on number 5,
Yes.
was it supposed to be 2 feet instead of 2 inches?
Yes, it was. I thought I had updated that in the system because you must have downloaded the homework really early. So I apologize for that.
So should we work it with 2 feet?
Yeah, it doesn't make
Okay.
sense with 2 inches.
No, I got a pressure drop of like 50 or a ratio of like 50.
Yeah, look, it doesn't make sense. So yeah, sorry for that.
Okay, thank you.
You're welcome. Any other questions? Blake, did you have a question?
I was asking what question that was that Levi.
Oh, problem 5.
Okay.
I think at one point it may have said 2 inches, but it should be 2 feet in terms of the initial diameter.
Got it.
Hey, Dr. Lopez, I was just going to ask, when is the homework now due?
Tomorrow at midnight.
Okay.
All right. All right, guys. Take care. Have a great day.
Thank you.
You're welcome.
Thank you.